As an example on assessment of aging structure, we will use Bakke bru in Flekkefjord, Norway. The bridge was built in 1844 and is one of the oldest suspension bridges in Norway. A structure from 1844 is obviously an aging structure and could serve as an example for this course. The span of the bridge is 55 meters, the width 2.8 meter, and the maximum allowable axle load is 2 tons. The question is, of course, if it can be used safely further. By the bridge, there is a plaque telling a bit of the story of the bridge, like you may find on heritage building like this one. So if we were the teams of engineers that should assess this bridge, if this bridge could be used further, what would we do? An assessment of an existing structure would typically start because you have some doubts about the integrity of the structure, or triggers as it is often called in standards. Such doubts can be anything from reported damages or deterioration, known changes to the loads it is exposed to, such as increased traffic loading, or just that the structure has exceeded its design life. In the case of Bakke Bridge, we can definitely say that it has exceeded its design life. When we have decided that an assessment is necessary, the first step of an assessment will typically be a site visit to the structure to perform a simple survey and or a review of documents related to the structure, such as design reports and drawings, to establish the design basis and the original state of the structure. If any or deterioration is identified, some simple calculation may be performed to see if this deterioration has any relevance for the strength and safety of the structure. If increased loads are found to be the case, simple checks if these loads are still within the design limits can be performed. Standards for surveying structures may be useful, and standards on assessment of existing structures can provide information about which surveys that should be performed and which documents that should be reviewed. Often, the original design reports will be the basis for this simplified assessment, with the purpose of evaluating if the structure is still within the initial design basis. Present design standards may also be used as support for the assessment. Since Bakke Bridge is a heritage building in Norway, some drawings do exist, and some information can be drawn from these drawings. Finding drawings for old structures is not always the case, and then a site visit with measurements and surveying may be a key task. A group of students used Bakke Bridge as their project in this course. From the site visit and from the drawings they found, these key geometric data was established. They also found some reports explaining many of the details on the bridge structure. The material quality used when the bridge was built is also a key question. We can find information that wrought iron from this time typically had tensile strength in the range 234 to 372 megapascal, yield strength in the range 159 to 221 megapascal, and a modulus of elasticity of approximately 193 100 megapascal. These values could be used, and maybe the lower values should be chosen to be on the safe side. Alternatively, we could take material samples and test these in a lab to obtain more accurate values, but we will talk more about that later. Another important question when assessing an existing structure will also be the material properties changing with time. For example, it is said that so-called Thomas steel, which is a bismuth steel, can experience reduced ductility and, as a result, an increased possibility of brittle fracture. The actual loading on the bridge now has to be established for our assessment calculations. In general, the traffic loading on bridges are increasing significantly with time. What was assumed to be acceptable design loads at the design point will often not be sufficient when assessing an existing structure for life extension. Our example, Bakke Bridge, has not been exposed to heavily loaded trucks for quite some time, and it was probably never intended to. Actually, it was more likely built to carry horses and their wagons. However, if Bakke Bridge is to be used further, we have to decide what loading it can experience. Another important source to look into is the experience and data from similar structure of the same vintage. Bakke Bridge has a sister bridge in Kalmuth, and any information we can get from this would be very helpful. The typical degradation mechanism for this type of structure and material is important to identify, as when inspection is performed, we need to know what we should look for. For steel structures of this type, we would typically search for signs of corrosion, cracking, and signs of wear and tear. Similarly, for a concrete structure, we would search for signs of chloride ingress, carbonization, corrosion of reinforcement with subsequent spalling and delamination of the concrete cover, freeze and thaw, cracking, erosion, wear and tear, and impact damage. For wooden structures, we would typically search for signs of rot, holes from insects, termites, ants and borers, crumbling, splintering, crushing, wear and tear, and fire damage. However, what we see in the inspection, what we call the damage type, is not the only important issue. Equally important is to know the effect of this damage on the structure. For example, how it reduces the strength of the structure or how it changed the rate of further degradation. And if we are to implement any mitigating measures to reduce further damage and deterioration, we need to know the cause of the damage. For some structural elements, simple indications exist of the loss of capacity with increasing degradation, which can be used in these evaluations. Here, an indication for the loss of capacity for a tubular structure member is shown as a function of corrosion damage. After these investigations are done, it is time to check if the doubts are still valid. If the doubts that we had is rejected, we can continue to use the structure without changes. However, if the doubts are confirmed, further inspections and material investigations and more detailed calculations will be necessary. Standards for how to perform material investigation of different materials should be consulted. More detailed inspections of the structure is an important element in gathering more information. Many inspection methods exist that can provide information about the structure and its geometry. The aim of the inspection will also be to uncover signs of damage and deterioration. Searching for early inspection reports are also important. Visual inspection is one of the inspection methods we can use, and with the help of some simple tools, it can determine large parts of needed information, and it can also determine some larger defects. The significance of any findings for the structure need to be evaluated. The student group looking at Bakke Bridge a few years ago used visual inspection and determined some corrosion damage, in addition to some deformation of one of the structural elements. They also observed the behavior of the structure during loading, the passing of a car. If the deformation of the structure is measured with accuracy for well-known loads, this information can be very useful in checking and improving the structural analysis. Correct modeling of the loads is obviously also important, with the correct load magnitude and placement. The load both at present and in the life extension period should be evaluated, particularly if it is expected to change or increase during the life extension period. When the condition of the structure, including any damage and deterioration found during the inspection, and the loads are established, it is time to do some structural analysis and calculations. Hand calculations are often more than sufficient, but computer analysis may in some cases be necessary. The purpose is to establish the loads and the stresses in the different components of the structure and normally check these against some capacity formulas, just like we do in design. However, now we have to make sure that we use the actual condition of the structure in the analysis and capacity checks. Capacity formulas for degraded structural members can be a bit cumbersome to establish and do not necessarily exist in standards, so some basic mechanics of materials may be needed. The capacity of structural members will often decrease with time, and we need to use the present capacity and the capacity we expect at the end of the life extension in our analysis. Such capacity formulas can sometimes be determined by analytical formulas or parametric equations, but often these need to be established by calibrated finite element analysis or model tests. It is worth noticing that the degradation may not be linear with time. As a result, finding results of earlier inspections can be vital to predict the expected degradation in the life extension period. Based on these investigations and calculations, we should check if the structure now comply with relevant standards. If it do, we may conclude that the structure can continue to be used unchanged. If the structure do not comply with the relevant standards, we may have to review different repair or mitigation options and seek to find reasonable method of repair and mitigation, if that can be sufficient to maintain the safety of the structure. Repair is here loosely used for anything that can bring the strength of the structure back to what is required, while mitigation is used as all non-repair measures that can still ensure the safety of the structure is acceptable according to relevant standards. A typical example of mitigation could be enforced load restrictions on the Bakke bridge, while repair of concrete structure could be jacketing as shown in this photo. Alternatively, we may choose to investigate the structure even further by advanced analysis, refined calculation, laboratory examination, field tests, statistical modeling, and reliability-based analysis. An advanced finite element analysis, as was done by Dr. Tech Olav Olsen, could be one such analysis to determine the capacity with more accuracy. Taking samples of the materials and testing these in a lab to get more information about the strength of the material is also an important way to hopefully get a more accurate value of the capacity established. In the worst cases, one of these links may have to be tested full scale and then replaced with a new. A full-scale test will give even more information about the capacity, but will only be done if really needed. An important topic of this course will be the different ways of doing the safety check, or verification as it is called in many standards. The common method is the partial factor method, where we determine a characteristic value of loads and strength and determine relevant partial safety factors and check if the design strength is greater than the design load according to the formula given here. An alternative that can be useful in assessment for life extension is a detailed probabilistic analysis, also called structural reliability analysis. In such analysis, all certain variables like strength, loads, deterioration, etc. are described by probabilistic distribution, and the probability of limit state exceedance is calculated. Then the probability can, in theory, and if all uncertain variables are correctly modeled, be compared with target probability values given in some standards. The student group that looked at this bridge some years ago assumed that all uncertain parameters could be modeled as normal distributed with mean value and coefficient of variation as given here. A note of caution, particularly the loads, would normally not be normal distributed, but that is a different discussion that we will take later. The probabilistic analysis is essentially to calculate the probability of the load S exceeding the resistance R. And we will look at different ways of doing these calculations during this course. Probabilistic analysis also allows for including new information in a consistent way. According to historic data, a tank crossed this bridge during World War II. This could give us some information on what the capacity of the bridge was back then, at least when the bridge was 100 years old. If this test load had occurred recently, we could have kind of chopped off the part of the probability distribution for the resistance that gave lower values than what was tested and redo the probability calculation. The method that we will use in this course for this is Bayesian updating and is a little bit more advanced than just chopping parts of the probability distribution, but in practice it is a bit of the same. Hopefully by now the structure will comply with the relevant standards. If the structure still fails to comply even after we have performed refined calculations, lab tests and reliability analysis, demolition may be the only valid option. If the structure is found acceptable, a suitable inspection and integrity management plan has to be established, ensuring that any deterioration or damage beyond what is acceptable is found, evaluated, and possibly repaired or mitigated. I hope this example gave a bit of an overview of what we want to achieve in this course. As a result of the discussion so far, the main topics of this course will be: how was the structure originally designed and erected, with what materials? How this type of structure and material typically degrade and change with age? How to detect such degradation and changes? How to evaluate and assess the strength of degraded structures? How to determine if the structure is sufficiently safe, taking into account the damage, degradation, and operations the structures has experienced. How to repair structures if needed, and how to maintain structures in the life extension period.